Good afternoon, everyone. Today's topic is regarding the advanced power system analysis and the control by using the Kunda system for connecting the large renewable power sources with the battery storage in the Australian national grid. So basically, this was submitted by the me and the Vinesh Patel. The basic aim of the project is to investigate, construct the southwards and the northwards of the Australian grid model with the added PV and the battery storage that can provide the power storage during the blackout time. So basically, in this one, the aim is very clear. Like in the grid, we are using the with the generation system, and the grid we are using the battery in the middle. So when there is a high peak, so battery can be the external provide the provide the electricity to the external load during the peak hours, and when there is off peak, so battery can able to charge during that time when the power is not used by the grid. In the introduction, we can see like how battery can utilize, and we can use that battery storage during the high peak. You can see in the picture like the battery storage is a type of storage that can be used for number of batteries to store the electrical energy. The power of the battery storage power plant is a order of magnitude which consume the less size compared to the hydro storage and any other form of storage. It's work on the very simple formula. Like when the demand is low, battery will charge during that time. But when the demand is high on the grid, that battery is supply the power to the that grid load. Introduction. So the basic aim of the project to investigate and construct the southwards and the northwards of the Australian grid model with added PV and the battery storage that can provide the power storage during the blackout time. In this arrangement, this is generated by the PV farm and the supply the power to the battery and the inverter, where the battery store the energy in the DC form and the inverter forward the supply transform by connecting with the AC form. This transformer converts the power to step up and provide the supply in the grid. This is the methodology. Like this is the pressure, like this is the step like how we achieve step by steps the simulation into our PSSA software. So first we have developed the Austrian grid model. Then after we have design the pump size. Then after we select the exact transmission parameter, then the fourth step will be connect the battery with oscillatory. Then after we perform the CCT to read the load flow. At the same time, we made the required file to perform this all the simulation. Then after we put the three-phase fault, then we got the frequency graph from the three-phase fault, and we have performed with hydro and without hydro, and in final we check all the things like exciter tuning, CCT, and the 30% rejection test with respect to NER modification. That's the load flow case. In the load flow case, what we have done is we have recorded the voltage before we adding to the PV and the hydro into the oscillant grid, and we can clearly see that the voltage is clearly in between 0.95 to 1.05 per unit. So we have added the PV onto the bus 401 into the case data. You can see there is a 401 NQ load, and into this first one we haven't added anything, so the load would be the zero here. The load and the voltage will be everything will be zero here, and then after with PV and the hydro we have added the hydro with connected to the 401 NQ load. So you can see the voltage of the uh, hydro and the PV here, which is nominal for operating condition, like between the 0.95 and 105. And after adding the hydro and PV, you can see all the voltage is regulated within the NER clues. Size of pump storage hydro machine. We have used 800 MVA battery storage in the project network for the generating enough reactive power, and the reasonable MVA capacity for 350 MV for battery storage is 400 MVA. While simulating the project network, double the storage capacity has been assumed, which lead to the network and capacity 800 MVA. To keep this reputation for the project network, we have chosen 350 of the battery storage with the 800 MVA. We accepted 400 MVA limit generator for PV framework generator. So total MVA generated is already defined here, like 400 into 2 equal to 800 MV. This is the comparison of other form of storage. Like we also compare like which is the best storage form to store the electrical energy while there is off peak on the load. So these are the 10 uh, latest type of the energy storage, like pump hydro storage, thermal energy storage, compressed air energy storage, small scale compressed air energy storage coupled with the natural gas storage, flow storage using the battery storage, fuel cell hydrogen storage, chemical storage, fa- flywheel storage, and superconducting magnetic energy storage. So this is this is the all the short form written next to it. And in this in this table, we also compare some popular like highest one and the lowest one with the compared to the battery storage. So you can see like energy efficiency is 99% for HS, and the EV like it's almost about the 99 and 98, whereas HES is a 42%. But where if you compare about the lifetime span, like lifetime span is pump hydro storage is a 50 years, whereas the lifetime span of the HES is a very less, about the 15 years. And the maintenance cost would be 0.9% for pump hydro storage, whereas the other all respectively similar except the HP and the HEC. All right, here also define the unit cost. There is a different unit cost, like some are the high, like HP is 870, and some are the low percent. Harmonics. So harmonics are the constituent of the current L, the voltage component, also frequency multiplied by integral and the base frequency. By integrating the harmonic current into the harmonic voltage enters, it shows like what is the old harmonics. We compare we compare with the harmonics multiply index, and then after we execute the harmonics, and we will see like what we get at the end. So the harmonics is generated due to the distortion into the some non-linear load like a motor drive, rectifier, fluctuator, lights, injecting currents, harmonics response, and the electronics equipment commutator executed to the limit as per the S51.6.A. Flicker. Due to the fast charging in the voltage level, problem has occurred which can be disturb the customer. Flicker is generally a fluctuation in the voltage, supply voltage, like sometime like there is a unregulated voltage within the grid. So so it can generate the flicker. Like in our project, we have defined the short term and the long term flicker, which is zero point 0.9 MV and zero point 0.7 MV, which has a HVEC zero point 0.8 and zero point 0.6 at the planning level. So in the flicker, we can see like we can avoid the flicker by regulating the voltage less than 10% in the good operating condition. And output of the solar PV affected with the fluctuation of the voltage from the solar rays. As we know, like solar is not a stable form of the storage. So it keeps fluctuating up and down. So that's why it's generate the flicker into system. Now the 30% load rejection. So the next few slides will be explained by my group partner Vinesh Patel.